Thank you. I just wanted to introduce our final speaker, Gurley Delacruz from UCLA, who will speak about game changer engaging physics learning beyond going through the motions.
Thank you, Jan. When Jan told me I was going last, I was a little upset because, you know, it always sucked going last. So he suggested, if you guys want, I could offer my services. We can go check out the expo instead. You can skip my talk. Any buyers, any takers? Ah, yeah. Oh, dope. So I guess I do have to talk. Okay, anyhow. As Jan said, I'm going to be talking to you about a project that I am working on with my team at UCLA. I'm not going to go and say everyone's names, but as you can see up here, there's a group of us from UCLA Crest. We're working with a game development company based out of Austin and Intific, and this project is funded by the Defense Advanced Research Project Agency, DARPA. So, you know, the popularity of physics puzzler games is unquestionable, right? As Lucien said earlier, all the kids want to build Angry Birds. Kids as young as 2, and even my grandparents are actually playing these games. And it's also clear that these games have, have the potential to be effective learning environments. But my talk is going to go over what we're doing with DARPA, and if any of you guys have ever had any funding from DARPA, you know that they tend to fund really sort of complex and crazy projects, right? And so we always call problems that are really difficult and almost unsolvable DARPA hard. So one of the things that, one of our goals is similar to what you've probably been hearing all day and all throughout the conference. You know, we're trying to design physics games. We're trying to find the holy grail for creating educational games. And what is that? That's to create a game that's really fun, similar to Crayon Physics, but to be able to make sure that children learn enough of the physics so that they are actually able to solve problems like this. So I think somebody for the last talk was asking about transfer, and Lucien's talk kind of touched upon this as well. But again, this is DARPA, and our DARPA wants us to do DARPA hard projects. So we're doing this game and targeting young children. We're targeting kids who are in kindergarten, 1st, and 2nd grade. So that means that in our game design approach, we have to minimize all of the reading requirements, as well as we're required to be able to create games that could operate in a diverse set of settings: classrooms, iPads, iPhones, with parents, which also means that we can't assume that they have access to sound. So to make matters even more complicated, the focus isn't simply just to get kids to understand physics. Really, what we're trying to do is to get kids to make this connection about problem solving, such that the sort of problem solving that you engage in physics, you know, the exploring the problem space, trying to examine what's going on, figure out different solutions, that also applies to other settings, social settings, especially social settings that are quite difficult, such as bullying. So our game approach needs to sort of create this connection between the two domains. Where we're at right now is revising our current prototype, and we're creating a game test bed. Our group within Intific built a prototype, and we've been play testing it. And from the information we got from those play tests, we realized we need to go back and revisit some of our design choices. And with our game test bed, what I'm doing in-house with our own game development team, we're creating research grade games so that we can engage in that sort of rapid fire testing that to help us be able to provide Intific with information about whether or not mechanics are effective or which representations are actually necessary. So for those of you who came to my talk last year, I was here also, not last, but I think I was 3rd to last. I discussed the approach that we tend to take at Crest in terms of our games and simulation design. It builds off of our work in assessment, and it's actually fairly similar to evidence-centered design, which you've heard referred to today. But what we do is what we design to the test. I am going to credit my colleague, Dr. Noel Enyedi from UCLA, because when he was looking at a process, he says, you know, what you're really doing is just designing to the test. So in doing that, we create what we call an assessment architecture. So it's essentially similar to a design doc or just set of design requirements. Our game developer gave us the CLAW report. I don't know if for all you game designers, you know what I mean. So it's really, really specific. And that's the standards that we hold ourselves to in our documentation. And our approach begins with figuring out what sort of thinking processes we want the kids to get into. So for instance, because we're focused on problem solving, we're going to want them to explore the quality of information that they're given and the problem space when they're first presented with a level or a task. They're going to need to identify which factors are relevant, which are not needed for their objectives. They're going to need to translate these problems using symbology and explore these sort of explore strategies. And then what we do with those sort of descriptions, those descriptions are similar actually to what Jan and his colleagues describe as the learning and assessment mechanics. We create operational definitions of them within the context of the domain, so within the context of physics. So for examining information quality, that means that we're expecting our students to be able to classify objects, the properties of the objects, surface materials, paths, and obstacles. They're going to need to be able to realize if we're having them deal with change friction levels to affect speed, the surface material or the slope angle of a surface is critical. And as you can see up here, actually will be able to produce representations and symbols of the underlying concepts. And then what that ends up becoming is this sort of basis for our task representation. So these are essentially it's essentially our game design, not only our game design, but also our assessment design, our instructional design, and we're also working with a children's book author. And so we've given them the same assessment architecture so that their narrative and their storybook and their characters can actually fit all of our specifications. So one of the things we've also learned while we've been working with different game designers is that these just narrative descriptions or just verbal descriptions, they're insufficient. So what we've begun to do is sort of we hold our assessment architecture to the same standard that we hold our own design of assessments. That is, we want to make sure that the level of specificity would allow different designers to be able to create similar and comparable products or artifacts. Right, so what we do is we actually give students, as part of this architecture, sample items, and I'm going to show you some of those items that we actually use, what we actually used in our pilot test, and the role of these items is also just to really make clear and very explicit what we're expecting our students to be able to do after they play the game. So. So for those of you who know educational psychology research, moving from inter-rater reliability really more like inter-designer reliability. That's sort of where we're at right now. So this is an example of an assessment item that we gave to first and second graders. And this was addressing issues of problem identification. The little robot guy, his name's Lee. And what students are asked to do is to click on things that are different between the two sort of segments. And so kids could either click or drag on the friction levels. The little arrows there are supposed to represent the level of friction of the pavement versus the grass. And some kids actually, of course, still also noted that the legs of the robots were different and that the surfaces that they were on were different. That was my little. And then in order to assess whether or not they can problem solve, if they can explore strategies and design solutions, we give them a scenario and ask them, for instance, to choose which side force they need to apply to, they need to push, they need to give to Lee so that he can go and reach the Rosen barrier or something, the prize that they're trying to get. So in this case, a child could pick a size of 2, 3, or 4, and vice versa. And we're also asking kids to use the physics laws that they're starting to develop in these physics rules to actually make predictions about novel situations. So we'll give them a scenario and ask them to predict how far they'll go or how fast they'll go. And one of the things we're looking at is having them just either draw it with a paint tool or on a tablet, gesture, and then use that gesture information as basis of our assessment. We are also building off of the work that Barbara White did with Thinker Tools. We're also expecting kids to, at the end, to be able to construct statements that model these physics rules. So because our kids, again, are K1 and 2, we decided to go with sort of like a tile-based approach. So they'll get a set of tiles that they can use to construct these statements, such as grass plus the force given to Emma would cause her to move. And the same icons and symbology that they use in the assessments are also going to be in the game. And then finally, our sort of hope and goal is that when they play these games, they'll also be able to generalize to other contexts. So we've been having kids recreate and play similar scenarios that they were given in the game levels with physical manipulative blocks. And we're also moving into, we're also extending the work we did with Noel Enyedi and Joshua Danish on the Spaces project, which is to have kids act out the physics. So it was actually very similar to Lucian's arrow, but we did it was very research grade, and we did it with first and second graders. So after we give the designers all these test items in the assessment architecture, what we do is we let them do what they do best, which is actually design. So we have them essentially gamify the stuff. And what we mean when I say gamify, everybody sort of cringes and thinks we're just going to add some bells and whistles and it's going to turn into Math Blaster. But no, we're actually taking a similar approach to what we did for our other game center, Center for Advanced Technologies in Schools, where the mechanics are actually inherently tied to the learning objectives themselves. So some of the mechanics we're exploring for things like problem identification are to, we're going to have them Okay, so for instance, with problem identification, what we want them to do is select and classify, right, objects. So that means that our game designers need to come up with a game that uses mechanics that require kids to select, which could mean taking pictures as data or tapping on actual objects. And they also have to classify those objects, which would mean, could mean putting them in different data fields or matching them with prompts. The explore strategies is actually pretty similar to what we are going to do, what we've done in the assessment tasks, just within the game context. Basically, kids are going to be given some sort of objective, and they're going to be asked to manipulate the resources given to meet that objective, and then as well as use their understanding to figure out to make predictions. For the problem translation, what we're thinking about is having the kids use the constructive statement icons as either codes to get into certain areas, or if there are little gatekeepers like trolls, blocking you from accessing the situation you need to fix. You have to be able to convince the troll that you actually know what you're trying to do and why it's actually going to work. So those are some of the things that we're thinking of, so that it's not separate and external to the game, but really sort of inherent in the game process. And finally, as I mentioned before, because we have to minimize the reading and sound requirements, we're exploring the use of iconography and representations as our annotations and mechanics. So we're going to use this both as how we annotate the gameplay as well as the resources themselves, with the goal to make the underlying physics explicit, and hopefully there'll also be we'll use some basic verbal text labels so that there may be some incidental reading learning that may occur. And we're also looking at using these as supports for other users. So something that Lucia mentioned that really resonated with me was the idea that trying to figure out how you can design these games so that teachers can use them. One of the things that we're thinking about is to have a version of the game where where there will be prompts for other users to sort of take turns to take turns actually reading to the players. So parents, this could encourage co-viewing or co-playing with parents and possibly allow for peer mentoring. So just an example of some of the icons and labels that we're considering. Right now, yes, we're modifying the existing game, and we're actually working with kindergartners, first and second graders to help us design these icons, because we can try and guess what seems transparent and meaningful for them, but in reality, they're going to tell you. It's working with them that's going to help us know how best to make things effective, students and teachers. And we're also similar to Lucian, we don't want to just have it be have an impact with just 3 teachers and 5 classrooms. DARPA really wants this game to go viral, so we are exploring crowdsourcing efforts to get lots and lots of data, and also help support us with our game development. And that's it. Any questions? Yes?
Can you kind of discuss what was the issue that you're fixing?
Oh, the issue we were fixing. Let me show you. Okay. The issue we were fixing was the idea that kids were able to play the game. That was no problem. They were able to. The game had 35 levels. I'm trying to find a screenshot. The game had 35 levels, and kids were getting through it in 30 minutes to 45 minutes. But the thing was that the kids didn't understand it. They didn't understand it was really. They didn't know they were dealing with physics. They knew they were making things move. They knew that they were changing angles and slopes, but that was it. So while that's useful, we had higher and more stricter goals. We actually wanted kids to be able to walk away with this and say, what I'm doing is I'm actually changing things. I'm changing friction levels by manipulating slope angle, or I am changing the size of the force I give them. We're trying to make that underlying physics that they're implicitly learning more explicit for them. And the current design that didn't have the annotations, that didn't have the sort of assessment mechanics built in, it wasn't supporting that. Yes?
What role does sort of like iterative experiment and repeated failure play in this system? I mean, can someone sort of be assessed by trial and error? Are people experimenting within the assessment space? And,
okay. For the assessment space, no. For the external assessments, we treat it just like a normal test. But within the game, if we have assessment levels, they come after they've already gone through their game levels. So we have our sort of big ideas, our physics big ideas chunked into suite of levels, where the first 4 levels, there's no you get no penalties for exploring. And in fact, that's what we're encouraging, because that's how they play the games, and that's how they can tinker. We want them to tinker. But once we know that once they've gone through all the levels and so have sort of reached that criterion level that we're expecting them to be able to do well, that's when we reduce their ability to have 20 trials. We might allow them to only do 2 or 3.